Dear ladies and gentlemen, thank you for joining and welcome to my presentation on the project XILforEV Connected and Shared X-in-the-Loop Environment for Electric Vehicle Development. My name is Christoph Lehne and I'm the Deputy Coordinator of this project. Let's start with a quick look on the main content. So our aim is to develop a methodology of connected and shared XIL experiments. This means that we create a test environment where various software and hardware platforms can be included. Therefore, we need high confidence models that are compatible with FMI, and also we need a machine learning layer which can automatically improve the real-time model accuracy and confidence. In the second half of the project, we will demonstrate the function of our test environment through various use cases, and I will show you two of them later. On the right side, let's have a look on our consortium. We had 7 initial partners from 5 countries, and now we've invited 2 additional partners to the project. First, it's important to define an architecture for communication, and our defined architecture you can see now. We have 4 layers. The top layer is the application layer, whereas the simulation or the testing facility, and the second layer we see in the optional functional mockup interface. Then we have the communication protocol, where we identified UDP as the performant protocol for data exchange in our case. And on the button layer we have the translation into VLAN or VPN, allowing us a safe and fast communication between the participating systems. What we see on the left side is the master, which is a full real-time electric vehicle model. And then we can include a number of N systems to substitute different sub-models in the master simulation. In the first step, we want to test our architecture in a local environment that takes place in Ilmenau. So we have these 4 platforms that are all located within the campus of the Technical University in Ilmenau, and we have distances slightly more than 1 kilometer. And these test benches, meaning a real-time full vehicle model running on a real-time PC, a brake dynamometer, electric hydraulic brake hill, and also a motor test bench, are connected through a virtual local area network that works within the university network. We experience delays between 2 and 5 milliseconds within these test environment. So you can see the local test environment framed in here, and the next step, if we think bigger, is to connect test platforms all across Europe between Zaragoza, Ljubljana, Delft, and the network that is already built up in Ilmenau. Communication tests on this are ongoing, and we also have further extensions in process that you can see here. The participating platforms in this case are connected using Cisco side-to-side VPN tunnels, which allows us a safe and encrypted communication between all the platforms. Like already mentioned, we have defined use cases for the demonstration of our functional environment. And for the local setup, we want to demonstrate this for the use case brake blending. Brake blending is the control of the distribution between regenerative and friction brakes, and a very relevant issue for battery electric vehicles. What we want to show is that we can analyze different brake blending strategies regarding, for example, the electric energy balance in a driving cycle like WLTC. We can do this using real powertrains included into the simulation and also a real brake dynamometer, so with a very high detail. For the remote use case, this is the test that will be performed all across Europe. We plan to test the integrated chassis control algorithms, including suspension test bench located in Zaragoza, and also including a driving simulator that is located in Delft. This setup allows us to benchmark different algorithms or various algorithms regarding driving comfort and stability in various scenarios. So let's have a look at the expected impact on research and development. Substantial is the reduction in lead time of electric vehicles through a higher integration of design within the whole supply chain. Also, an increased market penetration of energy efficient vehicles is expected. The improvement of the integration of suppliers, SMEs, and research into automotive product development can be reached through the concept as well. Speaking about general impact, we expect also new market and business cases. You can imagine, for example, a standardized protocol for remote test bench sharing, and very actual, so as a highly topical social benefit due to the situation in COVID. We see the reduction of traveling, since the engineer doesn't have to travel to the test bench, so he can use it remotely through our concept, through our new protocols. Regarding open research and open science, we expect that the concept enhances the exchange of know-how, and since not only test data and results are shared, but also test platforms. So this brings me to the end of my presentation. Thank you very much for listening.